In this video, we will continue looking at some properties of the cross product, and these properties will enable us to use the cross product to answer some questions about area and volume. But in order to get to that point, we have to start with a theorem. So let U and V be non-zero vectors in R3, right? Because remember, for the cross product, we need vectors with three components, so three-dimensional vectors. So let's say we have two non-zero vectors in R3, and theta is the angle between them. And again, we've defined what that angle is. So is the angle between them, right? Now, so this theorem has three consequences to it. The first consequence actually gives us a formula for the magnitude of the cross product, and this is what it says. It says that the magnitude of the cross product of U and V, that's equal to the magnitude of U times the magnitude of V times the sine of the angle between them. And you might look at this expression on the right and say, hey, that looks a little familiar. And yes, it looks a lot like an expression that we used for the dot product. The big difference being in the dot product, there was a cosine of theta. And now in this formula for the magnitude of the cross product, we have the sine of theta, right? Part B, it says this is a formula, a result that has to do with the area. The area of the parallelogram defined by U and V. So that area is, look at the formula, the magnitude of U cross V, right? So we talked about how we can use two vectors that are concurrent, right? They have the same initial point, and we can form a parallelogram based on them. But what this result is now saying, that the area of that parallelogram can be computed by taking the magnitude of the cross product, right? And then the third property is this. Now, if you happen to take the cross product of U and V, right? And remember, we're assuming that both of these are non-zero, but in some instances, you might take the dot product of two non-zero vectors, and you might end up with a zero vector. Well, again, this has an important consequence. So if the cross product of two vectors is a zero vector, so this is true if and only if U and V are parallel vectors. Right? So the only way the cross product of two non-zero vectors can be equal to the zero vector is if the two vectors are parallel, right? So in other words, and remember what parallel means for vectors is that they're scalar multiples of each other. So I'll just put that in parentheses. U and V are scalar multiples, right? Once you have scalar multiples, then the cross product of the two vectors would have to be equal to zero, right? So what I'm going to do is give you an outline of the sketch for part A. Most of it will be given, and then for B, the result is a lot easier to show. And then actually, once you have A, then it makes the other two results quite easy. So let's actually go through and look at the the proof of these. So let's start with part A. And what I'm going to do is I'm going to start with this expression and show that we end up getting the magnitude of the cross product. So I'm going to start with the right hand side. So I'm going to write this down. And basically just use all the properties that we know about vectors so far and somehow convert it into this. Now, the first thing I'm going to do, and I'll write some side notes over here. So you might remember this very important trigonometric identity that sine squared plus cosine squared is equal to 1. If I were to solve this for sine, then I'd have to subtract cosine squared. So I'd have sine squared theta is equal to 1 minus cosine squared theta. Then I would have to do the plus or minus the square root. So the sine of theta is plus or minus the square root of 1 minus cosine of squared theta. But remember, theta is the angle between the two vectors. And we know that the angle between two vectors is between 0 and pi, right? So since theta is between 0 and pi, then this means the angle is in the first or second quadrants, and the sign is always positive in both the first and second quadrants. So because theta, it has to be between 0 and pi, because that's how we define the angle between two vectors, then the sine of theta can be written as the square root of 1 minus cosine squared theta. And some of you might actually remember this as a trig identity. So that's what I'm going to do. I'm going to replace the sine of theta with the square root of 1 minus cosine squared of theta. So again, it looks like I'm going to be making things a little more complicated, but it will get us to where we need to be. Right, so we have this. All right. Now, why did I want to switch it from sine to cosine? Well, that's because as far as the dot product is concerned, we have a relationship that involves, vectors and the cosine function. So, just as a reminder. So remember, u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. That means if I solve this equation for the cosine of theta, so the cosine of theta is u dot v over the magnitude of u times the magnitude of v. Basically just dividing both sides by the magnitude of u and the magnitude of v. So what I can do is where there's a cosine squared, I can replace it by all of this squared, right? So let's do that. So this is equal to the magnitude of u times the magnitude of v times the square root of 1 minus all of this squared, which means the top is squared and the bottom is squared, right? So this will be u dot v squared over, and then this squared is the magnitude of u squared times the magnitude of v squared. Get everything under the square root, all right? Again, looks like things are becoming more complicated, and in a sense they are. But like I said, it's like we're taking the long scenic route to get to where we need to be. Now I have 1 minus this fraction. To subtract fractions, I have to get the common denominator. So the common denominator here is going to be the magnitude of u squared times the magnitude of v squared. So I'm going to put all of that under a square root. I'll have one big fraction with the magnitude of u squared times the magnitude of v squared. which means I have to multiply this 1 by the magnitude of u squared times the magnitude of v squared, and then minus, and then I have my dot product squared there, right? So I have the u dot v squared, right? Okay, so how does this help? Well, the fact that I now have a single fraction under the square root, I can use this property. If I'm taking the square root of a over b, well, that's the square root of a over the square root of b. So when I take the square root of what's in the denominator, the magnitudes go away, right? So, no, I'm sorry, not the magnitudes go away, but the square goes away, right? So I'll have the magnitude of u times the magnitude of v times, and then what I will have, I'll have the square root of the top, which I can't really simplify now. So I'll have magnitude of u squared, magnitude of v squared, minus the dot product of u and v squared, and then this is all over. When I take the square root of what's in the denominator, the exponents change from a 2 to a 1, right? The square goes away. So I have the magnitude of u times the magnitude of v. Now this helps because I have the magnitude of u, the magnitude of v here in the numerator. So that goes, because you know everything is being multiplied here, right? And then that goes. So all we're left with is that square root. So what do we do? Well, let's express the magnitude of u and the magnitude of v and the dot product in terms of their components. So these are two things that I can write in terms of the components of the vectors. So the magnitude of u squared is going to be u1 plus u2 plus u3, all of those squared. And then when I square the square root, it goes away. So I'm just left with this, right? And similarly, when I take the magnitude of v and square, I am going to have v1 squared plus v2 squared plus v3 squared. And then minus the dot product squared. Now, the dot product of u and v is u1 v1 plus u2 v2 plus u3 v3. So that's being squared, and all of that is under the square root. Now, this is where I am going to do a little bit of to get from this step to the next step, you have to FOIL everything out here, FOIL this out, collect 3 sets of terms, and complete the square. That would add like probably another 15 minutes onto this proof. So I don't want to spend all that time doing all that algebra. So I'm going to show you what the end result is after expanding, grouping, and completing the square. This is what you would end up with. And you would have u2 v3 minus u3 u2 squared. This is v2. This is v2. So that will be v2, and then plus, and then the next perfect square will be u3 v1 minus u1 v3. And then the last perfect square is u1 v2 minus u2 v1 squared. And what happens is if you go back and look at the definition of the cross product, this is the first component of the cross product. This is the second component of the cross product. and this is the third component of the cross product. And you look at what we're doing. We're squaring each component, adding them up, and then taking the square root. And that's exactly what you do to find the magnitude of the cross product. So it's quite the journey to get to this point, but it's an important result, because from this, right? So again, let me just kind of summarize and then write our QED. So the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times the sine of that angle. All right. So that establishes the proof of part A. For part B, I'm going to draw a picture now. So here's that parallelogram. So let's say I have U, that's U, and let's say this is V. So I have U, that's that vector, and this is V. Well, the parallelogram, if I complete the parallelogram, it will look kind of like this. All right, where again, this is U, this is V, and of course, the angle between them, this is theta. Well, to find the area of a parallelogram, what I would have to do is, if I could find this perpendicular height. So if I could figure out what this height is, then I would just have to take this height and multiply it by this length, right? And that would give me the area. That's the area of a parallelogram. Well, let's label the lengths here. So this vector has magnitude, whatever the magnitude of U is. And then, of course, this vector here has length magnitude of V. So let's see if I can figure out what this height is. Let's call it H. Let's call it H. But because it's a right triangle, again, I can use a trig ratio. So when I have my angle here, and then H in this case is the side that's opposite to the angle, and then of course the magnitude of U, that's the hypotenuse. So I have to ask myself, what ratio gives the relationship with the adjacent side and the hypotenuse side? That's the sine. So I could say that the sine of theta is equal to H over the magnitude of U. So therefore, H is the magnitude of U times the sine of theta, right? So what this tells me, the area, so therefore, the area of the parallelogram, so if I want to find the area of this parallelogram, what do I have? Well, that area is equal to that base, which has a length of magnitude of V, times the height. So I'll write this. It's going to be H times the magnitude of V. But I know what H is. This is H. H is the magnitude of U, and put that in parentheses, times the sine of the angle, and then that would have to be multiplied by the magnitude of V. But these are all real numbers, and I have the commutativity property, so I can write this as the magnitude of U times the magnitude of V times the sine of theta. And what is this? Well, this is what we just proved in part A. We showed that this expression is the same as the magnitude of the cross product of the two vectors that we started with, U and V, right? Yeah, so this one's a lot easier once you've established the result in part A. Part C, so this is the proof of part B, so there's my QED. For C, it says that if the two vectors are parallel, then the cross product has to be equal to 0, right? Well, if you think about it, so if, for instance, U and V are parallel, then it means that they either point in the exact same direction. So let's say that's V and U, or they point in the complete opposite direction, right? And so let's say that's V and that's U. Well, if they point in the same direction, then that means the angle between them is 0. If they point in opposite directions, then it means the angle between them is pi. But either way, when if I look at the magnitude of the cross product, which is the magnitude of U times the magnitude of V times the sine of the angle, again, which is what we proved in part A, if theta is equal to 0, or if theta is equal to pi, the sine of theta is equal to 0, right? So let's just kind of write this off to the side. The sine of 0 is the same as the sine of pi, which is equal to 0. So whenever the angle between the vectors is 0 or pi over 2, pi, the magnitude of the cross product is is equal to 0. So I'll say this. So when theta is equal to 0 or theta is equal to pi, the magnitude of the cross product is equal to 0. Well, if you think about it, since the cross product is a vector, right, the only vector that has a magnitude of 0 is the 0 vector. So this implies that the cross product has to be the 0 vector, right? So in other words, what we can do is, this is an easy way to check to see if two vectors, well, I wouldn't say necessarily the easiest way, but this is a way to check to see if two vectors are parallel. The other way is to see if there are scalar multiples of each other. Either way, I think the scalar multiples is probably an easier thing to check, but this shows you, again, an important property of the cross product. All right, so there we go. So that proves these three results. So let's definitely do an example to illustrate this. So this will be an example. So we're going to use so this is our problem. Find the area of the triangle with vertices at these 3 points. So this is a problem in R3. So there is P1, here is P2, it is -1, 0, 2, and here is P3, it is 0, 4, 3. So we want to find the area of the triangle with these vertices. Notice the problem doesn't say anything about vectors, right? Well, let's just go ahead and I'll give a sketch essentially, right? But I'm not going to put any axes. I'm just going to plot the points. Let's say these are the 3 points, and let's say this is P1, this is P2, this is P3, and I want to find the area of that triangle that they defined. Well, how can I make this into a problem with vectors? Well, what I can do is this. I am going to define the vector that goes from P1 to P2. I'm going to call that vector U. And then I'm going to call the vector that goes from P1 to P3. Remember, I need the two vectors to be concurrent, so they need to have the same initial point. So I'm going to call that vector V. And then what I can do, and I'll just do this kind of dotted, I can construct a parallelogram like this, right? And I can find the area of the parallelogram, right? And since it's a parallelogram, but I only want the area of the triangle, I can take 1/2 of this, all right? So basically, let me write down the expression that we are going to use in the end to find the area of this triangle, which is this area that we want. We don't want the full parallelogram. We only want a half of it. So this is what we're going to do. The area of triangle P1, P2, P3 is, it's 1/2 of the cross product, the magnitude of the cross product of U and V. All right. So there are a few steps that we have to go through, right? The first step is to find U and V. So let's go ahead and do that. So let's find U. Now, since none of these points, right? These points are not none of these points is the origin. So we have to use that head minus tail to find the components of the vector. So the components of U are, right? So it's the final minus the initial. So it's -1 minus 2. And then again, final minus the initial. So 0 minus 2. And then 2 minus 0. So I'm doing head minus tail to find the components of that vector. And that is -3, -2, 2, right? So that's the vector U. Next up, let's find the vector V, right? Again, use the same procedure, but now here is my head and it has the same tail. So to find the components of V, I have to take 0 minus 2. So that's the change in X. The change in Y is 4 minus 2. And the change in Z is 3 minus 0. So V is the vector -2, 2, 3. Good. So we have the two vectors now that essentially form the sides. You could either say form these two sides of the triangle, or you could say they define the parallelogram. Either way, we now have to do the cross product, right? So let's do the cross product of these two. And I will set up my 3×3 determinant, I, J, K. And then -3, -2, 2, -2, 2, 3. Then let's use our cofactor expansion. So I'll write down the 3 2×2 determinants that we need. So when I block out the first column, I'm left with -2, 2, 2, 3 times I, and then minus. Block out the middle column, I'm left with -3, 2, -2, 3 times J, and then plus. Block out the third column, I'm left with -3, -2, -2, 2 times K. Then let's write down the components, and I'll just put them in angled brackets. So we have -6 minus 4, we have that, and then comma, minus the quantity of -9 minus -4. So again, remember we're using our 2×2 determinant formula, and then finally -6 minus 4, because we have -2 times itself, and there's that minus in our formula for the 2×2 determinant. So here is the cross product of U and V. and we end up getting negative 10. Let's see. So in the outer pair of parentheses, we have negative 9 plus 4, so that's negative 5, but then that negative in front makes it a positive 5, and then finally we have another negative 10. All right, good. So that's the cross product. Next up, let's find its magnitude, right? So the magnitude of U cross V, well, we have the components of U cross V, so square each component. So this is negative 10 squared, 5 squared, negative 10 squared. Add them up and then take your square root. So what do we have here? The square root of 100 plus 25 plus another 100. So that's the square root of 225. And luckily, right, we have a perfect square. Yeah, so the square root of 225 is 15. So this 15, right, is actually, and I'll put this in parentheses just as a side note, this is the area of the entire parallelogram, right? That's 15, but we only want the area of the triangle, so we have to take a half of this. So therefore, the area of triangle, like I said, P1, P2, P3 is 1/2 of 15. So you could write that as 15 over 2 or 7.5 if you'd like as a decimal. I'll leave it as the improper fraction, and then it would be square units, right? So this, I love questions like this because when you look at it, it hits on, apart from like the computing the dot product and doing some basic vector algebra, it hits on a lot of the things that we've done so far. You know, finding the components of vectors, the cross product, and then the magnitude, and then this isn't really a topic that we've done per se, but it's recognizing now that we only want half the area of the parallelogram, so we end up dividing this area by 2. So hopefully you found that interesting. You saw a few proofs and then an example of using the geometric properties of the cross product. See you in the next video.